Nikhil Nanivadekar. I'm the project lead of Eclipse Collections. You can see the t-shirt I'm wearing. Eclipse Collections is a Java collections framework. It has nothing to do with the Eclipse IDE, okay? Like it's a very important disclaimer that I need to give. Like it has not, people will tweet at me, and they at me, they say at Nikhil Nanivade. I don't use Eclipse, I use IntelliJ, and I cannot use Eclipse Collections. And I'm like, folks, come on, it's a Maven dependency. It's a Gradle dependency. It's basically available in Maven Central, okay? Add that as a dependency, and you can use it. It has nothing to do with the Eclipse IDE. However, it has everything to do with the Eclipse Foundation, okay? So just a 30-second overview, like Eclipse Foundation does not mean only the Eclipse IDE, okay? Eclipse Foundation, it's a group of open source software which is under the Eclipse Foundation, and the Eclipse Foundation helps us with the the releases, the infrastructure, with management of the IP, etc., right? And that's why, and we would have just called it collections, but that doesn't make sense. We are under the Eclipse Foundation, so we call it Eclipse Collections. I develop in IntelliJ for Eclipse Collections, and that's the entire. I just read out the entire tweet, by the way, that I generally reply. But that's my Twitter handle, at Nikhil Nanivade. I generally tweet about my passions, which is food, hiking, traveling, and I sometimes tweet about Java. But it's generally among those. I don't tweet other than those things. But from an academic education perspective, I'm a mechanical engineer. I have a specialization in robotics, and I had not written even Hello World in Java till July 3rd, 2012. July 2nd, 2012 was my first day of employment. So that's when they, set me up with my access code and everything. July 3rd was the first day that I wrote Hello World in Java, okay? 2 years ago, I was inducted into the Java Champions group. How many of you know what are Java Champions? Okay, for the folks who don't know, Java Champions are essentially folks who are helping the Java programming language, and they are known in the community. And the way you become a Java champion is one Java champion nominates another Java champion, and then the rest of the group says yes or no, and if you get X number of plus votes, you get selected. If you get X number of no votes, you don't get selected. But that's pretty much it. And we have another Java champion over here. I think that's Gail. I think I don't see Hilmer, but Hilmer was here. Oh, he's here. He's also a Java champion. But enough of me talking. I think we have given people enough time to come in. It's 1:15. I'm on Central Time. That's why it shows 12:15 there. So let's get started with Spark, right? How many of you over here know what Spark is? Okay. So you guys all of you are going to help me with the presentation, by the way. Because the way I do a presentation is I like to do live coding more than slides. Because generally you start losing focus on the slides, and it will be the pace. I will want it's supposed to be an interactive session where if there are any questions or concerns or anything, you all can ask, and we can have a discussion kind of a thing. There are a few concepts which I do want to cover, and we will cover them. And if I start messing up, we have enough people in the audience who know about Spark, so they can help me out. How about that? Deal? Okay, perfect. Okay, so how many of you know what distributed processing is? Okay, can you tell me what is the most difficult thing about distributed processing? There's no right answer. It's fine. There's no wrong answer. Sorry. That's the right way. Okay, that's the right answer. And yeah, synchronizing the result. Anyone else? Latency. Okay. There's always eventual consistency. You can't help with that. That's a price that we pay for being highly available. So if I were to explain distributed processing, I generally explain it. First, I explain parallel processing, and we just had lunch, right? We had multiple tables, correct? and each table had 2 sides, right? You could go. That's parallel processing, where you have one table, okay? You have some work which is serving lunch, right? You have people coming, right? You have units of work who are going to serve themselves lunch, right? And now a table has 2 sides, right? So you can parallelize that, right? So one person goes on the left, the other person goes on the right, right? But now essentially you can only serve lunch from 2 sides on one table, correct? There are 2,400 people at the audience, at the conference. Okay, by the way, DevNexus is one of my favorite conferences. Vince, Pratik, and the whole Atlanta Java user group do an amazing job. So you're all like very lucky to have the conference. So, but that was a quick shout out. Anyway, so we have one table which has 2 sides, right? You have 24 people, right? 2,400 people who need to get lunch, right? So essentially what's going to happen is if we had one table, 2 sides, you'll have like 1,200 people on each side, ideally, correct? Now imagine this, how scalable is that? It's going to be painful, exactly, because then you'll have long lines, and then instead of having like, 40 minutes or an hour for lunch, you'll need 2 hours, right? So what did they do? They put multiple tables, right? They essentially distributed the way lunch is served to multiple places, right? And when we entered the hall, there was someone who said that, hey, go to the far end right, there is no line there. Go there, there's no line there. Go there, there's no line there, right? So there was someone directing us, right? We were all units of work, by the way. When right now, we just went through distributed processing when we ate food, okay? That is the exact same thing that happens in software programming or software solutions when we get a ton of data that we want to process, right? Let's say I have 1 million transactions to process, right? I'll parallelize the whole system and say, okay, it's going to run on, let's say 10 threads, 15 threads, right? We'll take 10 in order to make the calculation easier. You have 1 million transactions across 10 threads. So basically each thread is going to be responsible for how many? 100,000, right? So now, but what if each transaction takes 1 second to process, right? So what is, how long do you think it will take for the process to finish, right? How long? 100,000 seconds, exactly. Now, instead of, and this is all because there's only one hardware, right, which is giving you 10 threads, right? Now, let's say your SLA is that the whole 1 million transactions, they need to be finished in 10 minutes. I'm taking 10 because it's easier to calculate, that's why, all right? So what you do is you say, okay, I'm going to have 10 threads running, okay, in order for me to get done in 10 minutes, and let's say every transaction takes 1 minute. I know I said 1 second before, but let's make it easier for calculation. Let's say every transaction takes 1 minute for processing, right? And I've got, so how many threads would I need to process 1 million transactions in 10 minutes? It's a simple math problem, right? So, okay. 1 million transactions, okay? Right? 1 million transactions. 1 transaction per minute, okay? You need to process all of them in 10 minutes, right? So how long will it take? Oh, sorry, how many threads will take? Sorry? Exactly, 100,000 threads. Now, in order for you to have a system which can give you 100,000 threads, okay, you basically need one supercomputer, right, which will actually allocate 100,000 threads, and all the 1 million transactions are going to process at the exact same time, okay? Now, how many organizations actually have a supercomputer which will allocate 100,000 threads, right? Not many. So they came up with the idea that okay, we are limited by the number of threads that are available, okay? But we are not limited by the small, because you know, it's a give and take relationship, right? Right now, what is the problem? We need, technically we need 100,000 threads, correct? Right? So you can have 100,000 machines, right? Each machine just has one thread, right? These are very, very small machines, right? But then the problem comes is, when do we know when all the work is done, right? When do they shut down the lunch hall, right? I mean, they will shut down at a specified time, but let's say the rule was that every single person has to have had food, right? When do they actually know that the last person has come in, okay? So someone had said synchronization, right? That's one of the biggest problems in distributed computing, okay? Because now what you have is essentially, in order for you to get 100,000 threads, let's say you have a machine which gives you 10 threads, right? So technically, all you need is just 1,000 processors, right? Because each processor is giving 10 threads. Did I do the math correctly? No, right? Yeah, that was a test. It should be 10,000. Oh, sorry. Yeah. Okay, good. I was making sure people were paying attention, because come on, seriously, I can multiply. But any case, going back, so essentially you just need 10,000 processors. Now, making these small processors is much cheaper than having one huge processor. Also, because you have many small processors, let's say one of the processors goes down, it's easier to replace. You can also have some other processor pick up the work of this processor, okay? Now, at this point, everybody must be thinking, okay, is this like a preaching session by Nikhil about distributed computing? No, it's not. All of this is important for you to understand the reason why Spark came into, actually why Spark was invented, okay? Because there are multiple different frameworks which are there for distributed computing. One of them is MapReduce, like Hadoop MapReduce, right? Spark was pretty much built as after MapReduce, where the memory implications of MapReduce, they wanted to reduce it. They wanted to reduce the memory implications of MapReduce, and that's why in Caltech, Apache Spark was formed, invented, whatever you want to call it. Okay, so going back to what is Apache Spark. Okay, Apache Spark is an open source framework, okay, under the Apache Foundation, okay, and it is a way in which you can do distributed processing, okay. So today, the way rest of the session is going to look like is, we'll go through how, what exactly is Spark, how do you start a Spark shell, and what can you do in the Spark shell, and if you and all of this information that I'm giving is available out on the on the internet. It's just you're getting a one-stop shop here with all of these things and all the commands. You can download Spark from the Spark website, and that's what I've done. If you have a Mac or a Linux machine, it works right out of the box, no issues at all. If you have a Windows machine, the way I do, you have to do like a small fix, so to say, in order for it to work on Windows. And again, all that information is also available. Just Google how to make Spark run on Windows machine. You have to have and it's available on GitHub, where you just have to apply one small patch. It is safe, everything is fine, okay? And you can get Spark working, okay? Any questions so far? No? Okay. All right, now next. So 2, Spark as a framework is lazy, okay? What does that mean? Yes, it doesn't execute till you tell it to. It's a lazy evaluation. Like, how many of you have used Streams, the Streams API? Okay, Streams is lazy, you know that, right? Like, basically, it does not trigger evaluation, like that gentleman said, till it needs to, okay? How many of you know what is lazy evaluation and eager evaluation? I'm fine spending a couple of minutes explaining that. Okay, do you want me to explain it? Yes, no, yes, okay. All right, so there are 2 types of evaluations. One is eager evaluation, one is lazy evaluation, okay? What eager evaluation means, it's essentially the moment the program gets something to execute, it executes, okay? I always give this example about when I was a kid and my mom used to tell me to go clean my room. I used to say, yes, okay, never cleaned it, till actually guests came home, okay? And then I cleaned it. Now when my fiance asked me to go clean the room, I go immediately clean it, right? And that's because it's eager evaluation, right? So it's a different thing. Basically, what eager evaluation means is the moment you get an instruction, it is executed, okay? So if like I'm told, go clean the room right now, it is right now, okay? It's like that. Whereas with mom, it used to be like, hey, go clean the room. I'm like, yeah, I'll do it. So it's, yes.
So you don't need to tell how to clean or like how to do it?
Well, right now, I don't, like my mom and my fiance don't tell me how to clean the room.
For Spark.
Yeah, you will see.
About that.
Yeah, you'll see. So the question was, do you need to tell how to do something? We will see that. Like, just give it a second. Let me cover lazy and eager evaluation. So these are the two differences. Now, what lazy evaluation means, it's like, again, going back to my example, is when the guests were going to come, that's when I would go clean my room, right? Because essentially, now this is a terminating operation. If I don't clean the room, then I'm going to be in trouble, right? So I would go. It's exactly the same thing with lazy evaluation. When you get a terminating operation, and terminating operations are like reduce, count, toString, or a toList or something like that. That's why in the streams API, you do a dot streams, you add a filter, map, and then you do a collect, or you do a count, right? So in order to explain your question, answer your question, like how to do something, that is what is going in the filter, right? That is the operation. So cleaning the room is the operation. Now clean the room, okay? Use a mop, okay? Use a vacuum cleaner, right? That function which is going in, the lambda which is going in, that's telling how to do something. The same thing happens in Spark as well, okay? And Spark is 100% lazy, okay? Does that make sense about lazy eager? Okay, good. And
lazy evaluation is something that is under constraint, like you have to do it now, there's no other option, and you tell it how to do it.
I don't understand, but we'll come back to that. Give me a second. So okay, then the next one. By the way, can you all see the screen, or is it too low? I like to work on Notepad because I don't have to spend time in doing presentation like on PowerPoint. Okay, so the next one is, so for Spark, and again, we'll get into the code in like the next 5 minutes, but I want to like cover the concept so that you understand when I'm showing you stuff. One of the important data structures in Spark is called as an RDD, okay? Because the way Spark actually facilitates the lazy evaluation is by the creation of these RDDs, okay? And RDDs stand for resilient distributed data sets. I hope I got that right, Rodrigo. It's RDD is called as resilient distributed data sets, okay? And the reason why they're named as that is, we'll go in the order. It's called resilient, okay, because of a few things. It's resilient because it is immutable, okay? And what immutable means is you cannot change the data in it, okay? The only way to change something in an RDD is to create another RDD, okay? That's the immutable, functionality. It is also resilient because in case of failures, Spark can actually re-trigger the evaluation from a particular RDD, okay? And how that works, we'll see towards the end of the demo. The next one is distributed, because it is distributed because RDDs are actually passed around, okay? It is passed around the cluster, okay? And data sets, why do you think they're called as data sets? Why do you think they're called as data sets? They contain data, right? So they contain data. So what Spark does is Spark pushes the data around through this data structure of its own. It's called as RDD, which is resilient distributed data sets, okay? Is everyone with me so far? Did this make sense? Yes. Okay, perfect. Now, last concept before I start doing the demo is called as DAG, okay? What DAG stands for is directed acyclic graph, okay? Now, why is it directed, okay? I got the full form right, for the folks who know Spark, right? Is this correct? DAG is directed acyclic graph, okay, perfect. Hey, I can, like, I will not lie, like once I actually by mistake, I just finished giving a talk on dynamic programming. I did that and then I was like, DAG, that's dynamic acyclic graph, and like I could see people like be like, what? But that's why I always confirm, it's fine. So it's directed because it goes from one step to the other, It's acyclic because it does not have loops. And what that means is you cannot go back to a step. It always goes additive. It's always serial, sequential, okay? And it's acyclic. Sorry? Yeah, it's always forward feeding. Like, and again, that's where, just give me 1 second, I'll explain why they do it like that. And it's a graph because it is essentially made up of point, like it's made up of a diagram, so to say, okay? Now what they do with the DAG and the RDDs together is the RDDs follow the DAG visualization and they go from one system to the other, one cluster to the other, or essentially that's how Spark facilitates the transfer of data between multiple stages, okay? So anytime you create a Spark application, what the Spark DAG visualizer does is it goes and understands, it runs this assessment, says, okay, what all steps are there. It creates this directed acyclic graph, okay? So let's say, for example, you're doing step 1 to step 2, step 2 to step 3, and you need the step 3 to go back to step 1. It's not allowed because the DAG does not allow it. Otherwise, it will become a loop. So it's always additive. Does that answer your question? Okay.
Suppose in step 1, I have a wrong sort of data. Take a state, move forward.
Yeah.
I cannot go back, so I cannot change the state back.
No, everything is immutable. You cannot change the stage back. But what you can definitely do is, let's say something like, let's say you have 2 RDDs going in, and one of them is if it is true, the other one is if it is false, right? Like, again, Spark is completely lazy, right? So you don't have to worry about the memory on one side, unless it has reached a terminating operation and it has actually created the data, okay? That depends. It depends on the use case. But that's what Spark does is it uses the DAG or the directed acyclic graph to actually push the data around, okay? Does this make sense? Everybody with me? Like, we only ran through like 4 concepts so far. One is distributed processing, lazy versus eager, RDD, and DAG, okay? Anyone with me so far? Oh, sorry, everyone with me so far? Like, anyone at least. Okay, so let's get started. All of you can read the font, right? So once you download Spark from the actual Spark website, you get prepackaged things. So this is something which you can even, and I've got like no special software other than just Microsoft Windows and whatever you get it off the Spark website. And because it is Windows, it's doing that, okay? Also, I'm using Spark 2.2. I know that there are more recent versions of Spark, but the concepts remain the same, okay? So I wanted to upgrade, but you should never upgrade right before a talk. And interestingly, this was not working till an hour before because I tried to upgrade and then I'm like, no, let's go back. So I learned my lesson. Anyways, we are on Spark 2.2 right now, and essentially you can just run the Spark shell because that is something which is already available, and it's something which you download from the website itself. And you don't have to worry if you don't have an HDFS system or anything like that on your system. Like when you're working in on an actual production system, that time it's presumed that you'll have an HDFS system where you'll actually keep the data and Spark is reading out of that. Right now, we are going to use my laptop's hard disk, okay, as our HDFS system. Okay, and what Spark does is like Spark will bring up its own native, cluster, Hadoop cluster, so that you can actually play around with it. Okay, once you run Spark shell, a few things happen. One of the most important things is you see that there's a Spark context web UI available at a particular, IP. Okay, and what that is, you can actually open it in Chrome. Yeah. Why is okay?
Because this is simply running on your bare.
Yeah, on my bed, like nothing.
It's not like how at work we have a
No,
HDFS
there is
running and
no,
things
no,
like
there is
that.
nothing. Yeah.
So we can do this at home.
You can do it at home. You can do it from your living room, from like wherever you want, like on your train. Like it's like there's nothing special, and that's the reason why I don't have like because. Well, I mean, the same thing. I do a Kafka talk as well, which is like getting started with Kafka. That I literally start by downloading it during the talk. That like, hey, this is how we're going to do it because there's nothing special that I'm doing it. Okay, but and again, like this web page which is there, I'm going to zoom in so that we can actually see. So this web page which is there, this actually is a Jetty server which Spark brings up. And you get a UI, and this UI is important because you can see what is happening with your Spark application. Okay, right now it says an executor driver added. We'll cover what executor master worker is in a bit once I show you some of the commands. Okay, but this comes out of the box, and that's the timeline. We have not done anything yet. Okay, we just brought it up, and it brings up with that. Okay. You will see in a second. Like, don't make me go ahead of myself right now. Okay, you all can see. Sorry. So again, you have multiple options. You can configure which HDFS system you want to use. But okay, we are going to assume this didn't happen. All right, let me just quit and I'll restart it and I'll show you. If you read while the Spark shell is coming up, you can actually see that like there is no Hadoop cluster available, so falling back on a native Hadoop cluster. So see, unable to load the native Hadoop library, so bringing up instead, defaulting it. So it does all of that, and this is only in your local because like I'm doing it on my laptop, and I'm using my laptop's hard disk as my HDFS system or cluster. But in your actual production system, you will have your own HDFS technology. It can be Hadoop, it can be something else. It does not, like Spark supports most of them. Good question though. But anyways, going back to this, you're able to see the font, right? Or I can maximize. All right, so we are going to do two things, okay? One is I downloaded a list of all words of the English alphabet, okay? It's a text file, it's called words.txt, and let me actually check, yeah. So words alpha.txt, and let me open it up, and you'll see it has A to Z or Z, however you call it. But there are all of these letters which are there. The other one is the numbers.txt, which is nothing but numbers 1 to 9, okay? So far so good, nothing special, okay? So what we are going to do is now, we are going to read the alphabets first. I just didn't want to keep on context switching. That's the reason why I first showed you both the files. Now what we are going to do is we are going to read the file which contains the alphabets. Now if you remember before, I showed you that there were two important things. One was the web UI, and the other one right below it was Spark context is available as SC, okay? So that SC stands for Spark context, okay? What we are going to do here is you're going to say sc.text file, and these are some things which I have not written. It comes inbuilt with Spark. We are telling Spark that read the file words underscore alpha dot txt. Okay, that's it, one line. Okay, what it does is it says, basically my input file which is there, that is a type RDD of string. Okay, but now when we go back to our UI, and someone asked me that why do you need this UI? So you see here, because Spark is lazy, it has not yet read the file. Okay, it has not yet read the file at all, right? Because you cannot see any change in than what it was before. Correct? I refreshed the page like, and okay, there you go, refresh the page. Okay, nothing has changed. But now the moment I do input file dot, let's say, count, right, it goes and it says 370101, that's 370,701, you know, words in the file, right? And now when I refresh this, you will actually see that there was some work done. Okay, and the work was count. If we go in it, we get like, you know, event timeline and Dag visualization. But let's go to Dag visualization. It basically says that, hey, I had a text file. Okay, it kept every dot in it, it's actually an RDD. Okay, or a result. So here it says that I have an RDD which points to this reference, which is reading a text file, and then I did a and then basically it ends over here which says that I've done the count. Okay, that's fairly straightforward, right? With me so far? Now let's make it a bit more interesting by adding one more step. Okay, what I'm going to do is I have the input file. Okay, I'll reread it again because Spark is not going to do anything, it's lazy, right? So I read that, and then after that on input file, I'm going to filter it. Okay, and I'm going to filter the word if word.char at, okay, 0, right? Basically I'm trying to filter out the blanks. So if you see here, sorry, word.length, not char at, my bad. So word.length is greater than 0. Basically I'm trying to filter out any of the empty lines. Okay, it ended up creating another RDD. Okay, now I have not stored that RDD. Okay, so there is no way that I'll take it back again, right? So far, how many RDDs have we created in this cluster? 2, right? One is for input file, the other one is what I did right now, which was completely useless, right? Because I have not evaluated it yet. So Spark is not going to, you know, waste memory in actually doing anything there. Okay, but now if I did val words equal to input file dot filter, and then exactly the same thing that I did before, right? Word dot length greater than 0. Okay, so now this is somewhere, again it created an RDD. Okay, so now we have 4 RDDs, correct? With me so far, or I miscounted? We have 3 RDDs. Good. This again, I'm making sure you guys are up. So we have 3 RDDs. Okay, now I'm going to create a 4th RDD. Why? Because just now we have 4 RDDs, correct? Still Spark has not done anything. Okay, now what I'm going to do is I'm going to do words. Okay, not words 1, I'm going to do words dot count. Okay, now it's the same result, right? So how many RDDs will be in the system actually when we open the dashboard? How many? We started with 4, right? There'll be 3, or there'll be 2, or there'll be 4. Why will there be 2? Exactly. Correct. So when we go back here, let's actually see. Now firstly is we only see that there were 2 jobs because I only ran count twice. One was without the filter and one was with the filter, right? Now when we go in here and actually look at the Dag visualization, you see one was to actually read the file. Then this is called as the boundary, okay? Because between 2 stages, you need a boundary. Like if I add another filter, it will add another boundary, which is there, right? So technically, this is in this stage, this is the text file, okay? That's technically your 1 RDD. The second RDD is your filter here, okay? So you only are working with 2 RDDs, okay? The third one does not get created. And here's one more interesting thing, okay? Now, if I say, if I say this val input se.text file, and then I do a filter, okay? Filter word dot length greater than 0, okay? Dot count, right? Basically, I'm inlining the whole thing, right? So I got the input file out. Now let's see what happens out here. What do you think will happen? Will it be the same or different? Will it be the same or different? What do you think? Come on. Different? Hi, Doug. All right. Anyways, it remains the same because again, it does not matter because Spark is lazy. It is smart enough for it to like actually collapse those variables. I was not going to use that variable, then on, right? So that's why like it ends up saving memory in that way. Again, lazy evaluation actually helps in doing all of this. Yes.
So when you assign a variable, are you essentially just storing the instruction for how to store that variable, or do you metalize the actual data that would be created from sort of your list of commands?
Good question. The right answer is it depends, because if it is an RDD which has not yet been evaluated, it only has the reference that this is how Spark is going to get to it, okay? But if it has something like a count which is there, then that's because you remember I executed this at the end, right? Val input file equal to, and I did a dot count, okay? At that time, input file actually contains the count, okay? But it does not contain the data. It only contains the count. It does not contain those 370,101 words in it. Does that make sense? Does that answer your question? Yeah. So one of my very good friends while he was doing PhD, he told me, he's like, you know what, Nikhil, whatever you do, because I used to ask him like, hey, do you like this or do you like this, right? And he would say, and we were planning for his wedding, okay? And so like, he was like, do you like this or do you like this? He's like, yeah, it depends. Okay, one thing, like, hey, do you want Indian food or do you want like something else? Like, oh, it depends. Where do you want to have like, your party? Like, do you want to go here or here? It depends. Like at the end, like I lost it and I'm like, okay, can you give a definitive answer? He's like, I'm a PhD student. The last 5 years I've spent in saying it depends, because it depends on multiple things, like whether the scheduling works out, whether whether there are vegetarian options, etc., etc. That was his defense. But my defense is it really depends on what you're doing. Okay. But any more questions on this part of Spark? If not, I'll start the master worker and the actual application. We'll create a cluster and then we'll see how things change. We'll do the exact same thing.
Is it safe to say that if there is no terminate operation,
yeah,
you're going to have only the instructions?
Yes.
And if you have a terminate operation, then you're going to
evaluate. Yeah. Yeah, that is good. So to repeat Rodrigo for the audience, if there are no terminating operations, then it will only contain the instructions. The RDD will only contain the instructions. It will not act like Spark will not actually do anything. Okay. The moment if you have even one terminating operation, then it depends on which all evaluation Spark has to do. Like for example, right now we created 4 different RDDs, but we only use 2, right? That's the same thing. Okay. All right. So let me quit out of here. Quit. So now all of us saw what the Spark shell did, right? And essentially my Spark shell was nothing but my application, right? Whatever I was typing was getting executed, right? Now, going back to our discussion of distributed computing, imagine this, you have to process these 1 million transactions, but you have to write the same code 1 million times, okay, which is nothing but what imagine that that's the code that we have to write, input file dot read dot count, okay, that's all, but you have to write that 1 million times, right? How many of you will want to do that? So what will we do? Write a for loop and push it to different systems? I'm not kidding, that's exactly we should do. We should write a for loop, have every single node which is there and push that instruction to each of those nodes, right? You're writing the same code only once, correct? With me so far? That's exactly what you can achieve. I mean, not exactly that, but similar to that is what you can achieve when you're actually leveraging the whole idea of a Spark cluster, okay? What the Spark cluster is comprised of is master, okay, worker, and executor. So if you remember here, I know that I ended up exiting, so I hope it shows there. Okay, I'll show it to you in a second. But it has three different. Do you remember when I brought out the timeline? It said executor 0 added. Okay, all those who don't remember, there was something called as executor 0 added. Okay, good. Now essentially, what we are trying to do here is we are trying to understand how the Spark cluster works, because again, going back to the same point of like the exact same instruction which has to be evaluated 100,000 times, okay? Like you don't want to you're essentially going to create a loop of 100,000 and push the same instruction to every single node, right? That's what you achieve in this Spark cluster. The cluster has these three components. One is the master, the other one is the worker, and then the last one is the executor, okay? Now let's see what each of these components mean and what each of these components do. So master, okay, master is basically your referee, okay? It keeps track of the workers and the executors. And right now we are, for the purposes of this presentation, we are only going to consider there is one master, but you can also have multiple masters, and then you have a master of a master, okay, similar to your Kafka cluster, okay? But we'll have one master. Then you have a worker, okay? Worker is actually the system which does the actual work, okay? These are the people, these are the, you know, when I say people, these are the programs. And like now I bring up like a you know, everyday scenario. Like you have a manager, you have people working for a manager, right? And then you have a program manager, okay? Your master is your manager, okay? Worker is the people who are actually doing the work, and executor is your program manager, because executor is something, or you can call it business, okay? Executor is essentially the application which supplies work, okay? It tells what you're supposed to do. So the input file equal to sc.read file, that's your application, okay, or executor, right? So in order for our to equate it to our daily lives, master is the manager, worker is the people who are actually working, and executor is business or program manager, okay? Does that make sense? Or I completely lost the audience? Okay, good. All right, so we are going to do the same thing. We are going to see what I'm first going to show is some of the important nuances of when you start working as a cluster. Okay, so what I'll do is I'll bring up the master, and if I can find the commands, yeah. So, and again, I've not done anything special. This is all what comes, and what I'm saying is invoke the Spark class master, okay? And so it says successfully started master, and it gives you an IP address. It basically says Spark master at so and so place, right? Can everybody see it? Okay. This port is important, and I'm going to copy it, and I'll need it for the next commands, which is for the worker, and again, okay, and which is for the shell. But essentially, you will say, I've been elected leader. Can you all see the last line, right? Now, if you had multiple masters, then you have there has to be a master of a master, right? You have multiple managers, but still the managers have to have a manager, right? It's the exact same concept, okay? So now what we are going to do is, instead of starting a worker, I'm going to actually start a Spark shell, which is exactly what we did before. I'm going to take the Spark shell, okay, and I'm going to connect to the master, okay? So it will bring up the exact same, the Spark executor that we had brought before, okay? It will go through its own trials and tribulations, and okay, again, do you all remember how it was? Like, isn't it the same thing that is this deja vu? You had seen this before, right? You had SC, Spark context is available as SC, yeah. Generally, you just give it as a configuration, and you say that like you have all of these masters. Yeah, yeah. And then on top of that, like, you know, you can do something cool, like have like Zookeeper manage all of those things, and you know, there are multiple ways in which you can have like, or like for example, Mesos, Apache Mesos also helps you control this whole cluster and, you know, keep a tab on it. But it's slightly out of scope for this presentation. But anyways, so we have the web UI which is available, and we have the Spark context which is available as SC. So let me open the UI again. Oh, come on, not Google. Okay, so this is the jobs, okay, and if you see the event timeline, you'll see nothing is going on right now, right? With me so far, okay, nothing is working. But now if I go to master actually will say that like the master UI is available on 8080. Can you all see this, right? So let's open master UI, okay, and it says running applications. That is the executor which I added right now, okay, with me so far? Now let's do the exact same thing that I had said before, where we are going to read the input file, okay, and I'm just going to inline everything for the sake of at least this demo. We are going to, come on, we are going to inline this, and we are just going to do a count, okay, very simple, and I've hit enter. Now you'll see it has stage 0 plus 0 of 2, right? You remember there were two stages, one is reading and the other one is counting. It's exactly that, 0 plus 0 out of 2, right? But nothing is happening. Why is that?
Workers will do that.
Yeah, workers will do that. So basically we have a project, we have a master, but we don't have anyone to do the work, right? And if you see, okay, initial job has not been accepted, okay? So you get a good enough information that like, hey, no one is working on this because there are not enough resources, right? Now, I'll keep this going, okay? I'll keep this going. It will keep on attempting. Master will keep on, like the executor will keep on trying to tell master, hey, I've got this work, do it, right? Again, does that like remind you, you know, when like business or program managers come like and say, hey, I need you to do this. Like, oh yeah, we'll get it done. Yeah, we'll get it done. Yeah, we'll get. Does this sound familiar, or is it just me? Come on. Yes, no, come on. Yes? Okay, good. All right. So, okay. Anyways, so now what we'll do is we'll actually give a worker, right? We'll just do one, okay? And going back to the list of my commands, because I don't want to type the whole thing again, let me see if I can. I did it once in Morocco, and it actually was very beneficial for the audience when I was actually showing both of them on one on top of the other, okay? So this is the stage, that's the executor, okay? On my left, your right, okay? Let me start the worker, and once the worker starts, it actually sticks to the master, and it says, hey, I have master, and now you see, it actually did the work. You got the long, okay? You got the exact same result, okay? But because there were no workers available, was there. Okay. Does this make sense? So essentially, unless you have resources, you cannot do the work, okay? Does that sound familiar? Yes? No? Okay. All right. Now let's actually go see this part where now, do you remember previously there were no workers? Now we got one worker, we got the application which was already running, and now you will see that, okay, mine is an 8-core machine, 8-core 16 gig machine. That's where you see it is like, it's alive, it has 8 cores, okay? Good, right? Now, if I bring that same worker down, okay, and this is very important because what this helps you do as like someone who is writing code or managing this entire cluster is you have the ability to trace what is happening in your application, okay? Otherwise, imagine this, like you're stuck, you're waiting, like, hey, someone is going to do the work, someone is going to do the work. There's no one to do the work, right? How will you go? And you're like, yeah, I've been waiting for the last 3 days, all I need is like the word count, but like, no, nothing is happening, right? Like, it's exactly the same thing. But now what we'll do is we'll bring down the worker, okay? Let's say one of, and this is the worker, let me terminate it. Okay, so yes, yes. Now if I go back to the master, it still retains that, but now you can see the state has become dead, right? And this is very important, and you will see in a second why. Because what I'm going to do is, I'm going to bring back the same worker, okay? And while it is coming up, I'm actually going to start another command prompt. Okay, and okay, my worker is back up, and if I refresh this, you will see we got a new worker, right? Same configuration because it's my same machine, but essentially you got these resources. Now let us start another worker. Okay, are you all following with me, or like I'm completely like not making sense right now? Yes, there's a question.
Once we have a master, right? Shouldn't the master have application spin off the worker thread and like
Good question. So the question is like, once you have a master, shouldn't master like notify that it doesn't have any workers and you need to spin up workers, right?
it should automatically spin off the worker thread?
No, because no, not because, well, that is true, Spark is lazy, but again, it's separation of concerns, right? Master is only responsible for allocating the tasks to the available workers. Each worker has to attach itself, right? Because these are separate programs. Right now, imagine, like, just for a second, it's like, all of you remember, like, 11th, 12th grade physics when, like, they would say, consider an ideal weightless gas, right? You know what that means, right? What an ideal weightless gas means, right? Like, that's something which does not actually occur in real life, right? So it's the same thing. Consider a situation, okay, where the master, worker, executor are all on the same system, what we have right now, okay? But in a practical world, what happens is it's expected for redundancy and fault tolerance, your master, your worker, and your executors are actually separated. And they're separated by physical system boundaries. So your master may be working at on IP, let's say 212, your worker might be working at 214, and master is a separate program. It does not know how many resources you have available, because you might have just 3 masters, but you might have like 10,000 workers, right? So there's no connectivity. All 10,000 of them have attached themselves to the same masters, right? Does that make sense? It's separation of concerns, okay? Going back here, I'm going to, where was I? Yeah, I'm going to start another worker, and if you see, once I refresh this, you will actually see another of the same configuration because it's on the same system, right? But now, imagine this on different hardware. You could have one worker which just has 2 cores, otherwise, like you get the opportunity to fine tune. It does not matter how many cores are there, okay? But right now we have 2 workers, okay? With me so far? Okay, so now what I'm going to do is, going to do something which I've actually not done before in, oh, it lost, okay. Oh, this is master, okay. So master says that it lost executor. This is also master. Oh, sorry, this is the Spark shell. It says it lost executor. But the executor is essentially nothing but your worker, because we brought down one worker, you remember? Right? You remember that, right? Okay. So let's, after the whole connectivity is established and everything, now we are in this situation, okay? I'm going to read it, okay? And I'm going to add a small delay to just like a few words. And then we'll bring down one worker, okay? And we'll see what happens, okay? Good? So let's do that. Any questions on this so far? Are you all like getting any information or, oh, time? 3 minutes? Okay, sorry, I got like carried away. But this was the last section of this demo. Are there any more questions before I quickly show this? No? Okay, either I did a stellar job or a horrible job, and I'm an optimistic person, so I'll say I did a stellar job. But anyways, all right, so we got this input file, and okay, I'm going to filter out the word, okay, and if it is Z, then I'm going to add 1 second delay, okay, and at the end of it, I'm going to just count it, okay. So now, where did you? Oh. Okay, anyways. Okay, filter, this should be working fine. How many of you are like, what mistake am I making here? Oh, this should be fine. But anyways, imagine this was going, this went right. But essentially, let's actually try if I can do count, and no, that is not right. But okay, so the demo that I was trying to show is like if I had brought down one worker while the count was going on, the master understands that one worker is gone, okay, and it reallocates the job to the other worker that we have available, and it completes the job, okay. And the way it knows that like one of the workers is down is because one, it has a tab on it, and the second one is that when it creates the dynamic, the directed acyclic graph, which is that, you remember I had said by mistake I said dynamic, now that's all it's in my head. But anyways, like the directed acyclic graph, that time it actually understands that like, hey, at this stage, we lost the process, okay? And when you have multiple workers, what Spark does is it partitions its data set, and it only pushes that relevant data to a particular cluster. Now it knows that that worker had, let's say, data from A to B, okay? That's it. And you have lost that worker, right? So it takes that data from A to B, the reference which is there, and just pushes it to another worker. That's how it is able to pick up where it left off, okay? It does have to rewind one step, but again, it's better than rewinding the whole thing. It's like, let's say you have reached till 99%, you know, how many times it happens on Windows, right? Like it reaches till 99%, like saved or deleted, and then it says, oh, need to skip file, and then like you have lost everything, right? But not nowadays, this is like old Windows 98 probably. But that's the same case, like you can pick up where you left off with that. Okay, I hope you all enjoyed this. I enjoy presenting on Spark and Kafka and Eclipse Collections as well. If you like the talk, make sure you follow me on Twitter, just putting this back on there, and you can go to the website, take a look at it. Thanks a lot for attending, everybody. Thank you.